Hi students. So in this video, we're going to talk about the scientific method. So the reason why we discuss the scientific method as chemists or scientists, and like most scientists and philosophers, we seek truth. We want to know why things occur. That's the question. Curiosity and explanation. So the scientific method is pretty straightforward, although if you look at this diagram, it doesn't really seem so straightforward, okay? But one of the things is we're trying to explain nature, and we're doing this by making observations and then drawing. So a starting point might be in nature, we make an observation. And based on that observation, we might come up with an explanation of why it occurred. We might call that a hypothesis. And to kind of confirm that hypothesis, we would design an experiment. Now, once we design the experiment, we're going to test our hypothesis. And in some cases, we'll see that the experiment actually nullifies the hypothesis. A lot of times, it's easier to disprove something than to prove it. One experiment typically is not conclusive to any hypothesis. Some of you may have heard of null hypothesis, where you're actually wanting to disprove something to support another hypothesis. But you're going to conduct an experiment, and you might need to revise your hypothesis, or it might be confirmed. Now, if you do enough experiments, right, some of them may form into a law. And a law is basically, after your observations, after your experiments, you look at your results and you come up with a conclusion. And this conclusion is a law. And a law is going to basically tell you what's going to happen. Now, from a law, you can continue to make new hypotheses. The other thing is, a hypothesis can also go a little bit deeper than just explaining what will happen, and it might explain why things happen. And if it does that, then your conclusions of explaining why things happen become theories. So it's all intertwined. It doesn't have to be linear, as you can see in this diagram, but I want to make it as simple as possible. And when I test on this material, or when I tell students, I try to make it as straightforward as possible. So here we go. You're a scientist now. There's no turning back. Oh, heck. That's what you got to tell yourself. Oh, heck, what did I get myself into? Why did I decide to do this? Well, there's a couple of reasons why. You're curious. You want to know what's going on. So you make observations in nature. That's the O. You might draw a hypothesis, some type of explanation of why you're seeing what you see in nature. And because you're curious and you want to know what happened, you design experiments. And from your experiments, you draw conclusions based on your results. Now, there's two types of conclusions. One conclusion could be what will happen in future events. Based on your experiment and what you collected, your data and your observations of your experiment, you can explain what will happen. And eventually, if enough of these experiments are confirmed, the what becomes a law. You might be able to explain with your conclusions why events are happening, as opposed to just predicting future events. If you can discuss why it's happening with enough support from other scientists and enough experimentation and conclusions collected to find the same results, it might become a theory. So again, I want you to remember OHEC. So observations, what's an observation? Pretty much some of them can be made with the naked eye. I might see an apple fall from a tree. That's an observation. Others might require some instrumentation. I can use an electron microscope, or a microscope for that matter, to see much smaller things than my naked eye can observe. Observations usually involve the measurement with some type of instrument or a description of nature if you're using the naked eye. So an example, if I open up soda pop, it fizzes. That's an observation. Now, I did mention that the observations can be a simple description, like soda pop fizzing. Well, what if it's a measurement? Well, measurements are typically called data. So if I'm making measurements, it's referred to as data. Now I could have qualitative data, which again is more of a description. So an example, the soda pop fizzes, or a white precipitate was formed when I combined the two solutions. It's qualitative because I'm describing what I observed. Now, as physical scientists, as chemists, we also see this in physics and biology as well, even though it's considered a life science. We like to quantify things. Numbers mean a little bit more. 5.00 milligrams of white precipitate was formed. So now you're including a white precipitate was formed, but I'm giving a quantity to show just how much. So it's a little bit more, I like to say. So our emphasis, now it's not to say that we don't do qualitative measurements, we totally do, but we do a lot of quantitative measurements. And that's why after this video, I highly recommend going through the measurement videos to understand the different types of measurements we do. So what's an hypothesis? It's basically an interpretation. It's an explanation of what we observed. So how do we test our hypotheses? We're going to design experiments. What's an experiment? It's basically highly controlled observations designed to validate or nullify our hypotheses. So we have to have controls, and there's typically, different variables, the testing variable, the control, but overall the experiment is conducted in a fashion where we're observing things in a controlled environment. Now, the results of the experiment may require us to, again, reevaluate our hypothesis, redesign it, and make new ones, or it might confirm. The new or revised hypothesis must be tested through further experimentation. Again, one experiment is not conclusive. So when can all the experiments become conclusive or conclusions that result in something such as a law? So a number of similar observations can lead to a law. And a law is basically a brief statement that summarizes past observations and predicts future ones. So it's almost like a postulate. You can't defy it. So an example of that would be the law of conservation of mass. So the law of conservation of mass is widely known as, in the reaction, matter is neither created nor destroyed. We can only transform it. So whatever mass I start with is a mass I end with. That's an observation, and it predicts future ones. Another example of a law is a law of gravity. You can't argue that gravity is present. It's an observation from multiple similar observations, and it predicts future ones. Theories are a little more well established, right? So a theory explains why we're seeing the observations and the laws, okay? The theory is a broader understanding. It doesn't just tell us what, it tells us why. So what's an example? Atomic theory. Quantum mechanics explains why atoms and electrons behave the way they do. So again, what's the big difference between our conclusions in OHEC? The two conclusions were laws and theories. Laws answer what and predict future events. Theories explain why and require a little more work. So just remember, oh heck, I decided to take chem. Observations, hypotheses, experiments, and conclusions. And the two types of conclusions, again, are laws and theories. I hope this video helps. If you have any questions, you can leave it in the comments section, discussion board, or email me. And again, thanks for your time.